Hello friends, welcome to HP Vibrant Academy. In the last lecture we have discussed up to question number 14. So I will discuss question number 15 onwards in this particular lecture. So basically we are discussing the problems on the Gauss divergence theorem. So let's start our discussion on the questions. So what is given in question number 15? So it is given in the question number 15 is that if phi and psi are harmonic in V and del phi upon del n is equal to del psi upon del n on S, then what we have to show? Phi is equal to psi plus C in V. Okay, so basically we have to show phi minus psi is equal to constant. Okay, so what is given in the question? Given that first is phi and psi are harmonic in V. This means del square phi is equal to 0 and del square psi is equal to 0. Secondly, we have del phi upon del n is equal to del psi upon del n on S. Okay, so then we have to, based on these conditions, we have to show that phi is equal to psi plus C, that is in V, that is phi minus psi is equal to constant. Okay, this we have to show. Okay, so let us go back to the question number 14. We have seen that for proving phi is constant in V, two conditions are required. First one is phi must be harmonic in V, that is del square phi is equal to 0, and second one is del phi upon del n is equal to 0 on S. So if two conditions are satisfied, then we can say that phi is constant in V. So similarly, so we have to prove that phi minus psi is equal to constant. So two conditions that are required is, first one is phi minus psi must be a harmonic in V. This means del square phi minus psi is equal to 0, and second one is del upon del n of phi minus psi must be 0. Okay, so let us further expand this. So this is equal to del square phi minus del square psi. So this is, both are equal to 0. So this means this is equal to 0. So this first condition is satisfied. Let us go back to the second condition. Del upon del n of phi minus psi. So this is del phi upon del n minus del psi upon del n, and both are equal. This means this is equal to 0. So this means both the conditions are satisfied. Hence we can say that phi minus psi is a constant. So this means phi is equal to psi plus C. Okay, now let us discuss question number 16. What is given in question number 16? Show that, we have to show that surface integral n ds is equal to 0 for any closed surface S. So there is a closed surface S and n cap is unit vector along the outward normal. So we have to show this particular expression is equal to 0. Okay, so let us consider, let C be any arbitrary, let C be any arbitrary constant vector that is not perpendicular to surface integral S and ds. Okay, that is not perpendicular to this. So let us write down an expression C dot surface integral n ds. Okay, so this we can write as surface integral S C dot n ds. Okay, so using Gauss divergence theorem, we have f dot n cap ds surface integral is equal to volume integral divergence of f dv. Let us place the value of f as a constant vector. So C dot n cap ds surface integral is equal to divergence of C dv. So divergence of a constant vector is straight away 0. So this means this is equal to surface integral divergence of C dv. This is equal to 0 because divergence of a constant vector is 0. Let us discuss question number 17. So we have this as proved at r cross n ds for any closed surface C. So let us consider C as an arbitrary constant vector. Okay, so let us write down C dot, let us write down an expression C dot surface integral S r cross n ds. This we can write this as surface integral C dot r cross n ds. So C dot r cross n is nothing but scalar triple product C r and n. So this we can write as the order is C r and n. So this we can write as NCR. We can write this as NCNR. So this we can write as N dot C cross R. We can further write is that the order is immaterial in case of dot product. So this is C cross R dot N cap. So this is nothing but C cross R dot N cap ds, surface integral. Okay, so using Gauss divergence theorem, if we compare this with the statement of Gauss divergence theorem, f dot n cap ds, surface integral, is equal to divergence of f dv, volume integral. So this is nothing but, let us consider this as f. So f dot n cap ds, divergence of f. So this we can write as volume integral divergence of C cross R dv. So divergence of C cross R is nothing but, so using vector identity, we have studied that divergence of A cross B vector is B dot curl of A minus A dot curl of B. So similarly, this is R dot curl of C minus C dot curl of R, and curl of a constant vector is 0 and curl of R is 0. So both are 0. This means divergence of C cross R is 0. So this is nothing but 0. So this means C dot surface integral S R cross N ds is equal to 0. Okay. And we have considered C as an arbitrary constant vector that is not perpendicular to surface integral S R cross N ds. Okay, so if it is perpendicular, if C is perpendicular to this one, then the dot product of two perpendicular vector is obviously 0. Okay, so we have considered C as an arbitrary vector that is not perpendicular to this vector, that is surface integral R cross N ds. So this means this particular term, that is surface integral R cross N ds, is equal to 0. Okay, so if C is perpendicular to this particular vector, so this is straight away 0 because dot product of two perpendicular vectors are 0. Okay, so we have considered C as a vector, that is, we have considered C as a constant vector that is not perpendicular to this particular vector. Okay, so this means surface integral R cross N ds is equal to 0. As simple as that. Let us discuss question number 18. How we can solve this? Prove that surface integral del phi cross N ds for any closed surface. Okay, so let us write down this as, let C be any arbitrary constant vector that is not perpendicular to surface integral del phi cross N ds. Okay, so let us write down an expression C dot surface integral del phi cross N ds. So this is nothing but surface integral C dot del phi cross N ds. So this is nothing but C dot del phi cross N is nothing but a scalar triple product, that is C del phi and N. So this we can write as N C and del phi. Okay, so this is equal to N dot C cross del phi. So this we can write as order in case of dot product is immaterial. So this is nothing but C cross del phi dot N. So this is equal to C cross del phi dot N, C cross del phi dot N ds, surface integral. So using Gauss divergence theorem, on comparing this with f dot n cap ds, surface integral is equal to divergence of f dv. So let us take f as C cross del phi. So this is nothing but divergence of C cross del phi dv, volume integral. So let us expand this. So this is nothing but, so the using vector identity, divergence of A cross B is nothing but B dot curl of A minus A dot curl of B. So let us take A as C and B as del phi. So this is nothing but del phi dot curl of C minus C dot curl of del phi. Okay, dv, volume integral, and curl of a constant vector is 0 and curl of gradient of phi is also 0 based on vector identity. This means this is equal to 0. So we have C dot surface integral del phi cross N ds is equal to 0. Let us further simplify this. So we have C dot surface integral del phi cross N ds is equal to 0, and we have considered c as an arbitrary constant vector, that is not perpendicular to surface integral as del phi cross n ds. So this vector c is not perpendicular to this. If it is perpendicular to this particular vector, that is surface integral as del phi cross del n ds, so this means dot product of a two perpendicular vector is obviously 0. So we have considered c as an arbitrary constant vector that is not perpendicular to this particular vector. So this implies that surface integral del phi cross n ds is equal to 0. Okay, now let us discuss question number 19, how we can solve this. So we have the expression for the Gauss divergence theorem. Gauss divergence theorem as f dot n cap ds surface integral is equal to divergence of f dv. Okay, so let us consider f as b cross c. So we have the surface integral b cross c dot n cap ds is equal to volume integral divergence of b cross c dv. So this is nothing but divergence of, let us expand, divergence of b cross c. So this is nothing but c dot curl of b minus b dot curl of c dv. Okay, so curl of a constant vector is 0. So this is nothing but c dot del cross b dv. This is volume integral. And this is nothing but, let us expand this. So we have b cross c dot n cap. This is nothing but a scalar triple product b, c and n. This we can write as c n n b is equal to c dot n cross b. So this is nothing but c dot n cross b ds surface integral. So this is equal to this one, this particular expression, that is c dot volume integral, sorry, this is equal to volume integral c dot del cross b dv. Okay, let us further simplify this. So we have this as surface integral c dot n cross b ds is equal to volume integral c dot del cross b dv. So this we can write as c dot surface integral n cross b ds minus volume integral del cross b dv is equal to 0. Okay, so let us consider c as an arbitrary constant vector that is not perpendicular to, let us consider c as an arbitrary constant vector that is not perpendicular to the vector surface integral n cross b ds minus volume integral del cross b dv. Okay, so this c is not perpendicular to this particular vector, hence we can say that surface integral, hence we can say that this vector is equal to 0 vector, that is surface integral n cross b ds is equal to, since it is 0, this value is 0, this means surface integral n cross b ds is equal to volume integral del cross b dv. Okay, now let us discuss question number 19, how we can solve this. So based on the previous result, let us apply this particular result. So we have surface integral n cross b ds is equal to volume integral del cross b dv. Okay, so let us consider b is equal to a cross r. So let us put here. So we have surface integral n cross a cross r ds is equal to volume integral del cross a cross r dv. Okay, now let us find curl of a cross r. So first find a cross r. Okay, so we have, let us consider a vector as a1 I cap plus a2 j cap plus a3 k cap, and r vector as x I cap plus y j cap plus z k cap. So A cross R vector is I, J and K. This is A1, A2 and A3. Components of A vector and R vector. Let us write down. So R components of R vector is X, Y and Z. So X, Y and Z. So this is nothing but I cap A2Z minus A3Y plus K cap plus J cap, sorry, plus J cap A3X minus A1Z plus K cap A1Y minus A2X. Okay, now let us find, this is the value of A cross R vector is equal to, okay, now let us find curl of A cross R. So curl of del cross A cross R is nothing but I, J and K, components of del operator. This is del upon del X, del upon del Y and del upon del Z, and components of A cross R vector. So component of A cross R vector are this one and this one. So let us write down. So A2Z minus A3Y, this is A3X minus A1Z, and this is A1Y minus A2X. Okay, so let us further simplify this. This is I cap. Cross product, let us take the cross product. So del upon del Y of this one, this is A1, del upon del Z of this one, this is plus A1 plus J cap. This is del upon del Z of this one, this is A2. Similarly, this is A2 plus A2 plus K cap. This is A3 plus A3. This is nothing but I cap. This is nothing but I cap. This is 2A1 plus J cap 2A2 plus K cap 2A3. Okay, so this is nothing but 2 times of A1 I cap plus A2 J cap plus A3 K cap. This is 2A. Okay, 2 times of constant vector 2A. So this is nothing but, this is equal to volume integral 2A dV. Let us further simplify this. So this is nothing but 2 times of volume integral A times of dV. Okay, now let us take, it's better we can take 2A common. 2A and volume integral dV. So this is nothing but 2AV. Okay, so we have N cross A cross R is equal to 2VA. Okay, now let us discuss question number 20. The vector V is always normal to a given closed surface S. Okay, a vector B is always normal to a given closed surface. So this is parallel to our unit vector along the outward normal. This means unit vector is parallel to this B vector. That is, so based on the previous result, we have N cross B ds surface integral is equal to volume integral del cross B dV. That is, del cross B is curl of B. This means curl of B dV. This is volume integral. So N cross B we can, so since this B vector is normal to given closed surface, so we have B is parallel to N vector. So this means cross product of two parallel vector is 0. So N cross B is equal to 0. So this means this is straight away 0. So this means curl of B dV is equal to 0. Let us discuss question number 21. How we can solve this? So let us write down the expression for the Gauss divergence theorem. So F dot n cap ds is equal to volume integral. This is divergence of F dV. Let us take F is equal to rho times of V, where rho is a scalar and V is a vector. Let us put this in this particular expression. So this is rho V dot n cap ds volume integral, sorry, surface integral is equal to volume integral divergence of rho V dV. Okay, so we have studied in the chapter of vector identities. So divergence of phi a, where phi is a scalar and a is a vector. This is equal to del phi dot a plus phi times of del dot a. Let us take phi as rho and a as v vector. So this is equal to volume integral. This is equal to del rho dot v plus rho times of del dot v dv. This is equal to volume integral. This is equal to gradient of rho dot v plus rho times of divergence of v dv. Okay, and this is equal to rho v dot n cap. So this we can write as this expression we can write rho times of v dot n cap. So rho times of v dot n cap into ds surface integral. Okay, so we have to express this particular expression in the terms of surface integral. So this is nothing but this one. So we have expressed this particular volume integral in terms of surface integral like this. So the expression is surface integral s rho times of v dot n cap into ds. Okay, so this is the expression. Let us discuss question number 22. How we can solve this? Using divergence theorem, show that the volume V of a region T bounded by the surface S is given by this particular expression. Okay, so we have using Gauss divergence theorem, we can express the surface integral as x times of dy dz as this is nothing but volume integral del upon del x of x dx dy dz. This is nothing but volume integral dx dy dz. This is equal to dv volume integral. This is nothing but v. Similarly, surface integral y times of dz dx. This is equal to volume integral del upon del y of y dx dy dz. This is nothing but volume integral dx dy dz. This is equal to volume integral dv. This is nothing but v. Similarly, surface integral z times of dx dy is equal to volume integral del upon del z of z dx dy dz. This is nothing but volume integral dx dy dz. This is equal to volume integral dv. This is equal to v. So let us add all these three. This is equation 1, this is equation 2, this is equation 3. Okay, so we have this as surface integral x dy dz plus y dz dx plus z dx dy. This is equal to 3 times of v. So v is equal to 1 upon 3 surface integral x dy dz plus y dz dx plus z dx dy. Okay, so this we have to prove in question number 22. Okay, so now let us discuss question number 23, how we can solve this. So we have to evaluate surface integral x square dy dz plus y square dz dx plus 2z xy minus x minus y dx dy. Okay, so on comparing this with f dot n cap ds, surface integral is equal to, on comparing this with the basic expression for the Gauss divergence theorem, that is volume integral divergence of f dv. Okay, so we have the value of f as f is equal to x square I cap plus y square j cap plus 2z xy minus x minus y k cap. Okay, so we have the divergence of f as del upon del x of x square plus del upon del y of y square plus del upon del z of 2z xy minus x minus y. So this is equal to 2x plus 2y minus 2xy minus 2x minus 2y. So this gets cancelled. Sorry, this is plus. So this is equal to 2xy. So divergence of f is equal to 2xy. So let us place here divergence of f. So we have, and let us take this value as I. So the value of I is equal to 2xy. So divergence of f dv, and dv we can write as dx dy and dz. So this is nothing but dx dy and dz. Okay, so since S is a surface of cube, so let us draw a cube here. X, Y, and this is Z. So X varies from 0 to 1, y varies from 0 to 1 and z varies from 0 to 1. The limit are x is equal to 0 to 1, y is equal to 0 to 1 and z is equal to 0 to 1. So let us integrate this with respect to z first. So this is nothing but integration of dz is z and limit is 0 to 1. So the value of z is 1. Now we have 2 times of this is, now we have x dx and y di. So this is x square by 2, limit is 1 comma 0 and integration with respect to y square upon 2. This is limit is 1 and 0. So this is 2 into 1 upon 2 into 1 upon 2. This is nothing but half. So the value of this expression is nothing but half. Now let us discuss question number 24, how we can solve this. So by transforming into a triple integral, evaluate the value of this particular expression. So comparing this with Gauss divergence theorem, we have the value of f as f is equal to x cube I cap plus x square y j cap plus x square z k cap. Okay, and S is a closed surface bounded by the plane z is equal to 0, z is equal to b and the cylinder. Okay, so let us draw the cylinder like this. So this is x axis, this is y axis and this is z axis. So the equation of this base of the cylinder is x square plus y square is equal to a square. And this is bounded by the plane. So this plane is z is equal to 0 and this plane is z is equal to b. So z limit varies from 0 to b. Z varies from 0 to b. Okay, so let us calculate this. So the expression for the Gauss divergence theorem is f dot n cap ds surface integral is equal to divergence of f dv volume integral. So let us calculate divergence of f. So divergence of f is equal to, let us write down directly. So del upon del x of x square, this is 3x square. Del upon del y of x square y, so this is x square. Del upon del z of x square z, this is x square. This is 5x square. So the value of f dot n cap ds, let us take this as I. So the value of I is equal to 5x square dx dy and dz. Okay, so now let us use the cylindrical coordinate system. Okay, so we have the transformation from x, y, z to, let us take an arbitrary point here. So this is nothing but r, theta and z. So this is getting transformed to r, theta and z. And the differential of the Cartesian coordinate, that is dx, dy and dz, is getting transformed to dr, rd theta and dz. So from here dx, dy and dz is equal to r dr, sorry. So the product of dx, dy and dz is, let us take product of these three. So this is r dr d theta dz. Okay, so in the terms of polar coordinate, we have the equation of base is this one, x square plus y square is equal to a square. So the polar coordinates will be, let us further simplify this. So the polar coordinates will be x is equal to r cos theta, y is equal to r sin theta, okay, and z is equal to z. And the limit r varies from 0 to a, because the equation of base is x square plus y square is equal to a square. So the value of r varies from 0 to a, theta varies from, since it is a circle, let us plot this sorry, this is a cylinder, na? The surface is a planar surface. Okay, it's like a disc. Okay, so let us take an arbitrary element at an angle of theta to the horizontal. Okay, at an angle of d theta. So this is nothing but, and the position of this is at an distance of r. The radius vector is r at this particular point. Okay, so the differential is dr here, and this is r d theta. Okay, so this is area dA. So dA nothing but dr into r d theta. This is so, but for traversing this whole area, this theta must vary from 0 to 2 pi. Theta must vary from 0 to 2 pi. Okay, so theta must vary from 0 to 2 pi. So this we have already discussed in cylindrical coordinate, that is polar coordinate system, in the fluid dynamics. Okay, so now let us place the limit here. So we have the value of x as x is equal to r cos theta. So I is equal to triple integration 5 times of this is x is r cos theta whole square, and dx dy dz is r dr d theta dz. So this is equal to triple integration 5, this is r square and this is r cube. This is r cube, and this is cos square theta d theta and dz. Let us further simplify this. Let us place the limit here. So this is r is equal to 0 to a, and theta is equal to 0 to 2 pi, and z is equal to 0 to b. Okay, so let us further simplify this. So value of I is using cylindrical coordinate system. So this is 5 times of this is let us integrate, this is dr also, no, dr d theta dz. So this is r4 upon 4, limit is a and 0, and this is integration of dz is z, so limit is b, so this is b, and we are left with cos square theta d theta, and this is 0 to 2 pi. Okay, so we can multiply with 4 outside and divide by 4. So this is nothing but I is equal to 5 a4 upon 4b into 4, and this is 0 say pi by 2 cos square theta d theta. Okay, so let us further simplify this. So using cosine rule we can simplify this. So this is 4 gets cancelled, this is 5 times of a4 into b, and this is nothing but this is power is cos square theta d theta. So this is 1 upon 2 into pi upon 2. Okay, and this is 4 gets cancelled, so I is equal to 5 a4 b pi upon 4. This is nothing but the value of this particular expression. Okay, so now let us discuss question number 25, how we can solve this. So using Gauss divergence theorem, evaluate this particular expression. So S is the surface of cube. S is the surface of cube like this. This is x, this is y, and this is z. So x varies from 0 to a, y varies from 0 to a, z varies from 0 to a. Okay, so S is the surface of cube bounded by the coordinate plane. So this is the coordinate plane, that is x is equal to 0, this is y is equal to 0, and this is z is equal to 0. So this is bounded by the coordinate planes, and the planes x is equal to y is equal to a. So this is x is equal to a, this is z is equal to a, and this is y is equal to a. Okay, so these planes are bounding this. This surface is being bounded by these particular 6 planes. So 3 are the coordinate planes, and rest of the 3 are this planes x is equal to y is equal to z is equal to a. So now let us find the using the expression of the Gauss divergence theorem, f dot n cap ds is equal to volume integral divergence of f dv. So we have the divergence of f is equal to del upon del x of this one, del upon del x of x cube minus yz plus del upon del del y of minus 2x square y plus del upon del z of z. So this is nothing but 3x square, and this is minus x square plus 1. So this is x square plus 1 divergence of f. Okay, so let us place the value here. So we have, let us take this as I. So I is equal to triple integration x square plus 1, and dv we can write as dx dy and dz. Let us place the limit here. So x is equal to 0 to a, y is equal to 0 to a, z is equal to 0 to a. Let us integrate with respect to x first. So this is nothing but this is x cube upon 3 plus x, limit is 0 and a. This is and we have dy and dz. So the integration of dy with respect to y is y, and limit is a. So this is nothing but a. Let us place the y limit. So we have y. Let us write down one step further. So this is integration of dy. So this is y and limit is 0 to a. Integration of dz, that is z, limit is 0 to a. So this is a cube upon 3 plus a times of a dot a. This is I. So I is equal to, let us take a outside from here. So this is a cube. This is a square upon 3 plus 1. This is the value of this particular expression. So we have discussed up to question number 25. So we will discuss further questions in next particular lecture. Thank you.